Good morning, it's me again. I realized I made a mistake in a previous video where I talked about matter-antimatter annihilation, or more precisely, electron and positron annihilation. And rather than correcting the mistake, I did it in a comment on the previous video. I thought I sort of conclude the long series of videos with I don't know how I'm gonna call it, a pep talk about for colleagues who are interested in this stuff and who, just like me, think modern quantum theory, quantum field theory, doesn't make all that much sense, and who also believe that quarks and gluons, these virtual particles, contact forces, non-conservative forces, strong forces, weak forces, that ultimately that must be grounded, or can be grounded in classical electromagnetic theory. To start with that, yeah, here you can see actually the paper that gets me the most reads, and I strongly recommend you, if you're interested in my stuff, to read that. I talk about the original sin, I would say, that was made in successive high-level conferences, the Solvay conferences between the First and Second World War. Basically, I still think the first conference before the First World War had a lot of good concepts. The key to understanding things is really understanding what an electron actually is, and what a proton actually is, and what their antimatter counterparts are. And then based on that, I think you can build a whole new approach to modeling all these disequilibrium situations or disequilibrium energy states in high energy physics. So first you need to understand low energy physics correctly, I think, and that's sort of what I point out in that paper, where if you make that distinction between, when we think of frequencies, de Broglie's intuition that matter particles, just like light particles, must have a frequency. I think he didn't go down all the way and didn't distinguish or think of that a frequency may be a linear frequency or something, a linear feature like a photon or neutrino, field quanta, I would say. That matter particles, when you talk about a force must act on something. It acts on a charge, and the Planck-Einstein relationship basically tells us, a charge never sits still. It moves around, and it moves around in a way that is dictated by the Planck-Einstein relation. So it is a quantized thing in terms of its energy, in terms of its, it has a discrete size. But so once you interpret de Broglie's matter wave as, when you associate an orbital frequency with the charge inside matter particles, then all makes a lot more sense, I think, and a number of misconceptions, I think, where Schrödinger's wave equation is relativistically not correct. It's only valid for the non-relativistic lower energy limits. I think that's wrong. But I'm not going to talk too much about that. I did that in previous lectures. I just want to give you some courage, and myself too, actually, by pointing out that once you start digging into like a classical reinterpretation of equations, and that makes sense. I'm not dismissing everything that came up after the Second World War. I will talk about the W plus minus and Z bosons in a while. But yeah, this is a remark that has stuck with me. Philip Pearl is this is a paper written by a Russian scientist. My early inspiration for my own theories was a Russian scientist. Unfortunately, I lost contact with him. I think on the other side of the Iron Curtain at the time, they were doing a lot of good work, and that is coming up now a little bit, I think. So this Silagadze from the Institute of Nuclear Physics in Novosibirsk. As a historical reminder, they were among the first institutes who built actually an electron-positron collider and started analyzing what happens really. And their analysis don't don't invoke two charges disappearing and being transformed in fields. It's much more down to earth, and I'll talk about it in a moment as well. But he quotes an American professor in physics, Philip Pearl, from one of the oldest colleges in the US, actually, the Hamilton College, where in a series of papers and articles that got edited by Teplitz, he says the state of the classical electron theory reminds one of a house under construction that was abandoned by its workmen upon receiving news of an approaching plague. The plague, in this case, of course, was quantum theory. As a result, classical electron theory stands with many interesting unsolved or partially solved problems. I think a lot of these problems have been solved, or I point towards the solution in my own papers, and that's again work out what an electron and a positron and a proton and an antiproton actually are, and think of them as the forces inside as electromagnetic forces. I will talk about it in a moment. And then there's no need to assume, new forces, strong force or nuclear force. No, you can interpret that in terms of, classical electromagnetic theory. And once you've got these models right of your charged or neutral matter particles, but you think of neutral matter particles also as a combination of positive and negative charge, then things fall into place. What I don't agree with, but that's maybe a wrong word choice. Quantum theory, of course, makes sense. I recently dug into here the old 1911, before the First World War, the theory of radiation and theory of quantization, where this is this famous Solvay conference where you had over a dozen of Nobel Prize winners, and Einstein and Sommerfeld and Lorentz and so many others, and organized by Ernest Solvay, who actually came up with his own little theory. But what's in there is still makes sense, and it's worth reading to see where where things went a little bit wrong, I think. And but I'm gonna talk about it in a separate lecture or separate video. In my papers, I do have I'm not gonna pull it up now, but an analysis of the Solvay conferences, the most worthwhile contributions between the First and Second World War, and then sort of just before, after Lorentz died, actually, how he lost his battle with Born and Heisenberg, and not Schrödinger. Schrödinger stuck to his wave equation and a more classical concept of interpreting that wave function, not in terms of probabilities, but really in terms of the motion of a charge, as Dirac said it. We need to find the equations of motion. So that's all going to sound like Chinese. What I want to do and what I want to talk a little bit about, and I said, the only thing that's left for me is, to talk about high energy physics and say like, pair creation and annihilation. I have this paper here. I recommend warmly to read it, where you can look at pair production and annihilation as what I call a nuclear process, not in the sense that a nuclear or a strong force is involved, or a weak force, to explain disintegration, but again, what protons and neutrons really are, and how we should think of them, and if you think of them as a charged oscillation of charge, and a neutron as some kind of a neutron is then stable outside of the nucleus as a glue between two protons. If we have a nucleus with more than one proton, you know that just two protons without a neutron don't stick together. The neutron sort of acts as a glue, and I explained that a bit, in a very classical analysis of what Rutherford originally suspected, that a neutron may be a neutral by definition, combination of positive and negative charge, and unit charges, not partial charges like these quarks. So you need to read that paper, because I deconstruct there the idea of that charges just get destroyed. You need to combine that with this paper. Probably, do we need the nuclear force hypothesis? Do we the problem was really that inside of the nucleus the force is indeed very strong. So people had this intuition, it can't be the electromagnetic force, it's much stronger. But in this paper, I build on, it's an Italian polymath. He produces an awful lot of papers in various fields, and he conceives nucleons as dipoles, magnetic dipoles. But as I said, I think protons do carry charge, and neutrons as well. So it's an electromagnetic dipole. The advantage of this conception is that a dipole field can be very strong at close range, and it's asymmetric, but it's a conservative field, conservative forces. The electromagnetic force is there, and that's a conservative force. And so when you work out, and this was quite revealing for me, the forces that you would have in such a dynamic dipole fields do amount to the binding energy between nucleons, and that's where I'm gonna talk about now in the little notes I made to prepare. So my hypothesis is that there is really no need to assume that there is a thing like a strong force or a weak force, strong interaction, weak interaction. For me, weak interactions, decay reactions, just labeling it as a force or an interaction is a philosophical misnomer, in the sense that when you talk about a force and interaction, it's things that attract each other or things that repel each other. And in the case of beta decay or alpha decay or gamma decay in nucleus, we the analysis in terms of quarks and gluons and weak force, there's absolutely no need for that. And you will say then, okay, what's the classical theory? Well, the classical theory of that has been around forever, and now I'm gonna pull up this what's an old website actually of the University of California observatories. It's a network of research units of researchers in California, thinking about cosmogenesis and a lot of other things. And they have this Lick observatories, which was founded by not Bill Gates, but another rich man. And that's they make these analyses where where do the elements come from, and we know that they're born in they're made in the universe in these furnaces that are stars are, and helium, and so this nucleus synthesis becomes hydrogen becomes helium, and then it's all about building nuclei that lower the energy of the total system and the total atomic system, and that happens, and we know that this is the interesting graph, that there's sort of an optimal point. It's called the iron peak, which is a very stable element, and then it continues. Elements with lower atomic weights are gonna fuse together in heavier and heavier elements. But you've got that actually. You know, iron is the is sort of what the universe might return to when it cools down. And it's not to say that heavier elements aren't stable, and that's what I'm gonna go now to. Is you know, this is the periodic table of elements, the classical one from the American Chemical Society there in the corner. And then one, I should have mentioned the source that lays out these elements in a different way and says, like, you know, up to lead, basically, with atomic number 82, you know, we have a stable elements, or at least an isotope of these elements that is stable. With stable, I mean, it doesn't fall apart. We have two slightly radioactive elements there, technetium and promethium. These are now synthetic elements. They once were probably created in these you know, furnaces, the stars, but now we can only produce them in labs, and they're stable but not so stable. The color codes are there, so the life half-time of technetium is you know, between 800 years and between no, it's larger than 4 million years, but you know, 4 million years in the universe is not an awful lot. So for all practical purposes, natural technetium, you won't find it anymore, because our planet is older than 4 million years, a lot older. But we can synthesize it, and it's quite stable as a synthetic element. Promethium is you know, more radioactive. Why are these two radioactive elements there in a series of you know, up to lead that is stable? Well, I don't know. That's got to do. I don't know, but I'm sure it's got to do with the structure, you know, the electron shells, and the way an atom, what an atom actually is. And that's where again, I think modern theory goes wrong in terms of, you know, isolating decay processes from you know, where they are happening inside of an atom, or you know, a molecular structure. So I'm not gonna dwell too much on that, but the common sense thing I want to say, you know, when you read about alpha decay, let me pull up the Wikipedia articles on that, is and that's actually funny. Alpha decay, you know, it's it's particles. An alpha particle is a helium-4 nucleus. A beta particle, you know, sounds mystical, but it's an electron that gets ejected, or a proton. A positron that gets ejected, and other nuclear processes. Well, yeah. A neutron, that's what Schrödinger said, neutron and protons, you know, I said neutrons act as a glue within inside the nucleus, so we have these neutron proton interactions, which I put here, and they involve, of course, the exchange of radiation energy in the form of you know, quantized field particles, photons, which again are sort of linear oscillation, I think, in 2 dimensions, and neutrinos, or I said, you know, sometimes neutrinos, antineutrinos. What's the difference? Well, it's their spin, and you know, think about spin in a very literal way, the way you know, curl and divergence of a field is organized, and this is a 2-dimensional or 3-dimensional oscillation. So I'm not going to talk too much about that. Read the papers, but I think sort of you know, if you get rid of the idea of particle, really, and you think of you know, a structure, an electron as a structure, as an oscillation of charge, you think of things as, you know, in a dichotomy that is not like boson fermions or hadrons and what have you, baryons. And no, just think of charges and fields and how they work together and form stable structures, or in high energy physics, how you know, a disequilibrium state might look like. A disequilibrium state will also involve you know, charge whizzing around and fields surrounding those charges that move around. But yeah, the disequilibrium state situations or states do not respect the Planck-Einstein relationship, and that's why they're unstable and fall apart in the end in constituents that do respect the Planck-Einstein relationship. So I'll show that here. So when you sort of want to study and you're interested in cosmogenesis, because that's ultimately, my interest as well. What is reality? What is matter? What is mass? What is energy? Then go for these more classical interpretations. I would say go back to classical electromagnetic theory and read about, because that's something I think after the Second World War people realized, is that when you're going to study physics, fundamental physics, you also need to look at astronomy and all these processes that a whole other line of scientists are studying. The conditions in the universe, what's happening there, expansion, contraction, temperatures, background radiation. And so the main thing to look for is indeed sort of study that combustion cycle, I would say, in stars. So then you will learn everything about nuclear reactions. Nuclear reactions also study study how breeder reactors work, and how nuclear fission works, and or how the hydrogen bomb actually works. So there's so much stuff that is purely is going to teach you what a binding energy actually is, and it's electromagnetic in its nature, and look at sort of these particle reactions in terms of particles you can understand, helium-4 nucleus, which is a stable thing, an electron or a positron, which is also a stable particle, and sort of what happens in between all these metaphysics, I would say, of quarks, gluons that we can't observe, but that somehow in some mathematical model appear as I don't know, factors that you have in a matrix equation or an S matrix. Then you don't need that. And so I refer here to my ResearchGate papers on nuclear reaction, nuclear forces, and in which I basically these nuclear processes are just plain electromagnetic processes that take place. Now the big thing, of course, is the mistake I made in my how should we imagine that like an electron and a positron come together? Because that's in high energy physics the main question I have. This Dirac process. Dirac imagined that we have an electron in which compared to a positron is in a positive or negative, depends on your polarity, a positive energy state, a negative energy state, and they come somehow together in a zero energy state, and that's charge annihilation according to Dirac. Now the Dirac process, and it's reversed, the Breit-Wheeler process, where two charges, where two gamma rays, highly energetic fields would come together and sort of out of nowhere produce a pair of opposite charge. There's no experimental evidence for that, and so what I show here is sort of my question that remains unanswered. Then what happens actually if an electron and a positron come together? So if we imagine them in my electron model, which is really that model where let me write it down. We have the E is mc square relation, right? We have the Planck-Einstein relation, the reduced Planck, and then a frequency, which is an orbital frequency. And then we have, C here, if we interpret that as an orbital velocity. Then, if it's an orbital velocity, it must, be the product of an amplitude, radius, and that orbital velocity. And if you combine that, mc square is ma square times the orbital frequency is h times that orbital frequency. This, by the way, makes perfect sense. We have two linear oscillations, and that makes the charge go round and round, and the charge sticks in place because it has this magnetic field, electromagnetic field, mainly magnetic field, so it's like superconducting current. If you combine that, then you get the classical, not the classical, Thomson interaction radius. A0 is h bar divided by mc. And I said the point-like charge inside that is whizzing around has, that's the classical electron radius, which was very confusing. Electron has a radius. Well, the point-like charge has a radius which is equal to alpha, defined structure constant, times h bar. And it also has, of course, a Bohr radius, which is 1 over alpha times the Compton radius. But so that's the one that matters here. So we have an electron, and I said we think of it as a structure, as an oscillation of a point-like charge inside. That's the big confusion that Dirac had when they were talking about Schrödinger's Zitterbewegung hypothesis. So the electron goes round and round. Its spin is up or down. When you want to, its magnetic moment, we have a south and a north pole. It's like two tiny little magnet that gets created, and then we have the positron. When these come together, I think they should line up, just like two magnets, south and north, and then here also south and the north and the south come together. Let me clean up my sheet. So what happens, according to Wikipedia, when you go to the article on positronium, where is it here? Yeah. It, in most cases, they annihilate directly and produce these gamma rays, which I'm going to talk about. Are these real gamma rays, or are they? Where does the charge go when these pairs of gamma rays are created? But you can read about that, and so in most cases they annihilate directly. In some cases they do form an unstable positronium, should call it particle. About 40% of the cases, or 10% of the cases actually, with a mass that has, which is just over 1 mega electron volt, which is not enormous. It's 2 times the equivalent mass of the electron, and a lifetime or an energy state that decays very quickly. Less than, between 0.12 nanoseconds to up to 142 nanoseconds. I think these experiments all need to be revisited. I believe they are real. They surely measured, pairs of what they said, gamma photons coming out of these things. But I wonder, these experiments were done in the 70s, and then in the 60s, and in the 70s, this concept of W plus minus and neutral Z bosons came up, and I think these are like photons, but they're not like photons. They aren't photons, and they aren't probably bosons either, because bosons you can pile one on top of each other. And I said I don't think charges just really go sit on top of each other. And in my model also, an electron has energy, and I use the energy partition theorem, which was also used in the 1911 conference to explain a lot of stuff. Well, I say half of the energy of an electron is the kinetic energy of that classical point-like charge that whizzes around at the speed of light. So half of that is kinetic energy, and the other half is the energy in the field, the electromagnetic field. So that's sort of a potential energy, but it has an equivalent mass. Total mass consists of 2 parts, and so if the charge disappears, well, then can't have kinetic energy, and so then that positronium or the gamma rays that come out can't. They will only carry half of the energy. I said a positive and a negative energy. If they combine to produce a zero energy state, where does the energy go? So I think it goes somewhere, and these bosons that later disintegrate into stuff we know, electrons again and positrons and other matter particles. I think they've carried the charge all along. And so I do not believe, that's the question asked, do 2 charges really annihilate and turn into fields? I don't believe that. So that's the Dirac process. I think that's a purely mathematical thing, where indeed you use the superposition principle and say opposite fields. But as you can see, we don't have opposite fields here. It's like 2 tiny magnets that we're clicking together, or 2 rings from a solenoid that we are putting together. There's no destruction of field energy there. On the contrary, we get a magnet with twice the strength. And And I also think that you know, these two charges don't sit just on top of each other. In that image here on Wikipedia, where the electron and positron you know, don't go and sit on top of each other in that brief intermediary disequilibrium state is probably valid. And when sort of the positronium disintegrates, I think these gamma rays aren't real photons. They carry charge, and it might be this neutral Z boson. I think that's the only idea that makes sense from the electroweak theory of Glasgow and others. So can two charges really just sit on top of each other and form a zero energy state? I don't think so. We don't see that annihilation of energy, and so I don't think you know, this energy conservation, and so I also think there's charge conservation. Let me clean up my sheet. So the thing though is, yeah, what happens then really? Yeah, where is this point like charge? If it doesn't sit on top of each other, where is it gonna be, even in this brief disequilibrium state? How it's gonna move through space and time? It's not gonna move at the speed of light, but as you know, these electron-positron colliders, you know, they accelerate these electrons and positrons, and so there's a lot of extra kinetic energy there. So how does the charge then move through space-time? Again, I'm not gonna. I think I have no other slide here. No, I could have had another one where maybe let me go to that. Here in this paper where let me look for the diagram of Giorgio Vassallo. It should be somewhere. Where you know, if you accelerate an electron, some of the orbital velocity becomes a lateral velocity in the direction of motion. And here we have that. And then you see the size of the electron becomes smaller. Of course, we're going to move the electron as a whole. So there's no, here in this diagram where you have, you know, the black ring is our original electron in the stationary reference frame. So if it starts moving, or our reference frame moves in regard to that station, the reference frame of the electron, then it's going to appear the relativistic effect that you know, the radius of that oscillation is going to become smaller, and we have like a point-like electron. But you know, what we forget is that in these electron-positron colliders, we're adding energy, and so that energy has to be somewhere. And that's sort of a model I haven't worked out, but it must be something like that, because you know, what you see here in this graph is that if we accelerate an electron, it becomes like photon-like in the sense that it becomes point-like, but it's not a photon. It keeps carrying the charge, the unit charge that is in that point-like charge inside, which has a definite radius, and it's not very small. The fine structure constant is 0.0007 something, so it's almost 10% of the Compton radius. So it's not small at all, and I think we need to go that way, and that's where I'm gonna end my lecture, and refer you, like, look around. There's a lot of is Philip Perl a mainstream researcher? He's a very respected professor of physics, and he thinks, you know, these new theories don't make sense. So is that mainstream, non-mainstream? I mean, he's got a tenure, he's professor emeritus, and so there's a lot of guys like him out there, and so I sometimes think it's the mainstream theories that don't make sense. Of course, that's my opinion, but I feel, you know, when you're like me, cheer up, because you're in damn good company. Guys like you know, Philip Perl and the guy who wrote this paper. I haven't checked his CV or anything, but you know, this is a very respected Russian institute, and I think we're gonna see in the coming decades sort of you know, a new way of approaching things, and this new way is gonna be the old way of approaching things. You know, yeah, distinguishing between, you know, what is between charges and fields, and recognizing that the Planck-Einstein relation implies that, you know, a charge is never at rest. Heraclitus was right. Everything is motion, and motion of what? Well, motion of a charge, and motion of you know, fields. Then dynamic fields are the motion of what? Well, yeah, that's field is a mystical and not so mystical concept. Think of it as a charge, as a force without a charge to act upon. And what charge? Well, there's only the electric charge. There's no such thing as a weak charge or a nuclear charge or a color charge or whatever. So that's the other thing with these modern, you know, quantum field theories and whatever. They revert to a concept that I think of as medieval. You know, contact forces that ferry around, that work through virtual particles that carry momentum and energy from one real particle to another real particle. You know, that's medieval. You don't need contact forces. Contact forces are not there. It's charges and fields that interact, and the fields say where the charge go, and the charge, its motion says how the fields is going to look like. And that's the one point I want to point out is that that's something that is true, is what Feynman says. You know, this electron model of mine, that, yeah, that's sort of like a superconducting loop, and you know, we have this steady electromagnetic or magnetic field that keeps the ring current steady. But you know, when you go below the scale of that electron, the h bar divided by mc, 0.386 femtometer, then now Feynman asked the question: can you really analyze that as a continuous ring current? No, because you have that particle, and so yeah, kinetic theory. You need a different kind of math, and that's maybe the last thing I'm gonna show on again, going to the grandfathers, I would say. When you look at sort of the table of content, and the kind of questions in the discussion, I don't know if I have the table of content. There it is. Yeah, it all talks about, yeah, developing appropriate kinetic theories. Theory cinetic, well, the equipartition theorem of energy, entropy. I don't think that's the table of contents. Where is it here? Here. Bam bam. The formula. Yeah, it is there, but it's a report. But it's about kinetic theory, motion, and one of the key things that come back in the discussions after these eminent scientists, you know, all Nobel Prize winners in the early 20th century, present their stuff. It's about, you know, our electromagnetism works with the differential equations. You know, when you have these discontinuities, can we use the differential equations? I give a nuanced answer to that. But it's clear that, you know, we need a new math to model disequilibrium states, to model unstable particles. And that math, I will readily admit, I haven't found that math, but I am happy that I have an idea of what, you know, how charge moves around in an electron and a proton. You know, it's two and versus three-dimensional oscillation. And that's my hypothesis, and explains the interaction radius between electrons and protons and photons and neutrinos, and it provides sort of you know, this twin. An electron will couple with a photon, a proton will couple, you know, when interactions happen with that, and neutrinos are involved, and neutrinos are like three-dimensional photons. That's probably why they don't travel at the speed of light, etc. But that sort of, these models make sense. My worldview makes sense. But have I worked all of the math? No, for sure not. And so that's the positive message I would like to give. Do like these guys go. This paper from last year. Yeah, look at these old problems in classical electromagnetic theory, I would say. But yeah, what is an electron, and you know, what equations were there to and concepts were there for what they mention here, the concept of the electromagnetic mass of a charge. So that's that kinetic relativistic mass that a charge in motion has, and said it's half of the mass of the mass particle of a proton of an electron as a whole. So look at these things, and yeah, I hope this lecture made somewhat sense. It did for me, because I need to get back at my day job. I have another contract as an IT project manager, and yeah, that will consume me again. I had a brief holiday, and now it's back to work, daily life, discipline. So no time for fooling around and talking about things like this. So I wish you a very nice day, and I hope this inspired you to keep doing what you do if you watch these kind of videos, and that's to think for yourself and yeah, develop a kind of a worldview and also a view on theories, cosmogenesis, because it makes a big difference. That's something I want to add. When I can't read a theory that talks about a quark gluon soup. I can read a theory where they talk about a plasma of charges and highly energetic electrodynamic fields and sort of what would happen there. But that's a theory then where charges may annihilate and you may have this transformation. I'm not saying it's not possible, I'm skeptical, but in the high energy limit where charges do become fields and fields become charges, but it's going to be unit charges. The constants of nature, Planck's constant, the speed of light, the unit charge plus or minus one. The electric constant, the magnetic constant, what's in Maxwell's equations. These are the bedrock of physics, and once you abandon that, you talk about quark gluon soup, then it's really like what's that scientific philosopher that doesn't make much sense, but said, anything goes, any theory goes. Well, no, because if any theory goes, there's no agreement on any fundamental formula that allows you to distinguish between good and bad theories. It took hundreds of years to develop Maxwell's equations. It took less time, but 40, 50 years before Boltzmann and Planck, they were each other's enemy, but sort of could agree on, there must be Boltzmann more like a constant of that terms what entropy is, and pops up everywhere in macro situations, and Planck, who developed that H, Planck's constant, first as a Hills variable, but said, energy states, there's no continuum there. There's discrete energy states, and of course it depends on the situation. We're talking an atom or a molecule, or we're talking an electron or a proton itself. That's sort of when you let go of that, when you think, well, nature's constants aren't constants, and in these high energy situations, everything gets undone and becomes loose, and these constants may or not be there or shift. Gravitation may look different. That sort of it's not going to get you anywhere, and that's where I pity the people who are really into these mainstream development of supersymmetry models, quark gluon theory, tuning it further and further, seeing what because these the weak force or the weak interaction and the strong interaction. Well, we're going to develop a gauge for that, because the math with non-conservative forces is that gauge matters, and it makes your tensors look completely different. An electromagnetic tensor looks the same, whatever gauge you use in electromagnetic theory. And that's sort of where, the forces stay the same. When you have these theories where, depending on the gauge, we get a very different outcome in terms of the forces that appear. And of course, you'll have that, you have a relativistic space-time framework, so forces do look different in a different reference frame, but this is something from an entirely different order. This philosophically, I would say ontologically, because that's my interest really. What are the foundations of physics in terms of the concepts? A bit like what Kant states, time and space are categories of the mind. Well, I try to do the same thing in physics, just like, Kant. Well, he lived long before Einstein, and Lorentz came up with their with Lorentz transformation. I realized that some quantities that appear to us, energy and momentum, linear or angular, they appear differently in a different reference frame. But there is something absolute, the constants of nature, the unit charge again, the fine structure constant, which is derived actually, the speed of light. These are absolute constants, and they don't depend on your reference frame. And based on that, I think, and that's the good thing about the 2019 revision of the system of SI units, Système International des Unités, it's all in there. And it's clean. In that sense, for me, it is the end of physics. It's just, we need to, what he says here, that house under construction that was abandoned, well, we need more workmen to finish that building or that house, because it's a beautiful house. And yeah, I don't know what happened. Between talking about the Solvay conferences, the Einstein didn't go to the first or second one after the World War because the German scientists weren't invited. So you had a lot of competition. Breit also complains about, after the Second World War, where he said there's no friendly international sphere of cooperation anymore between scientists. I need to look up what Breit said. He was from Russian or Polish origin, but a famous American physicist. And he regrets that. And you can see it. I have in my papers, I talk about the first Solvay conference after the Second World War, which is dominated by a fairly violent exchange between Oppenheimer and Dirac, and you can see they talk alongside each other, and that's not good. And I think it's one of the problems why we don't have a unified theory anymore. We talk about grand unified theories, but there's a lot of smoke, a lot of smoking guns, but there's no bullets, there's nothing definite there, and it's kind of tiring to see that these theories become ever more complicated, because anything goes, and so nobody says, well, this is it then. And I can see this is it. We need to finish that building, that classical theory combined with the Planck-Einstein relation gives you all of classical quantum mechanics. Maxwell's equations model, continuous things, continuous fields, charge densities, continuous currents. Well, when you combine it with the Planck-Einstein relationship, you have an electron-proton model, and these two together give you everything. And that's, for me, that's a bit the end of physics. I said, I hope to see the house finished. There's only a little work to be done, and then a lot of painting, I think, to make it look really beautiful. So I wish you a nice day, and I said, I will disappear from the scene for a while because I've